we can begin. So people will sort of keep dropping in over time. So we have 75 minutes, and if whoever is attending, if you want to ask a question, you can just unmute yourself and do it. That's usually, that works pretty well for the most part. And apart from that, we might have about 5 or 10 minutes after the talk to have, if in case there are any more questions. So, you can interrupt during the talk if you want. All right, with that, I'm going to introduce our speaker, Sauvik Banerjee from IIT Bombay, who's going to give us a talk about latent factor models for causal inference. And anytime you want to begin, Sauvik, it's yours.
Yeah, okay. Thanks so much, Kanishka. And Economics and Planning Unit at ISI Delhi, thank you for having me over. So this paper I will be presenting today, it is already a published paper earlier this year. It's joint work with Anirban Basu from the University of Washington. However, although bulk of the work will be from what has already been published, but there is scope for extending this work. So I'll be glad to speak with anybody who's interested. And also right at the end, if there is time, I would like to devote a little bit of time in terms of some ongoing work I'm doing, extending this framework. Okay. So, okay. So in terms of background, most of us who do any applied research, we at some point or the other, we have to deal with issues of endogeneity, or where there can be potential sources of omitted variable bias or reverse causality or measurement error, which essentially can lead to biased and inconsistent estimates. Okay. And so in that context, especially from a policy perspective, it's very important to try to get causal estimates, but we know that they are, it's very difficult to get one unless you have, say, a perfect randomization, for example. Okay, so one of the methods which is often used is instrumental variables approaches, which are widely used in empirical research when one of the covariates of interest is endogenous. Okay, so using appropriate instrumental variable or variables, if there may be more than one can obtain consistent and unbiased estimate of the treatment effect, although it is well known that the instrumental variables estimator is less efficient than the OLS estimator. So, yeah, was there a question? No? Okay.
You just carry on.
Okay. So in practice, for applied researchers, we know that finding suitable instrumental variables is always a challenge. So the validity of the instruments is typically very difficult to test, and it's untestable if you have only a single instrumental variable. However, you can test for the strength of the instrument, which is not difficult, but claiming that the instrumental variable, in fact, is uncorrelated with any unobserved factors that might be correlated with your treatment assignment and with the outcomes of interest, that is typically not an easy task. Okay, so strength of the instrument is easy to test, but the validity of the instrument is non-testable in the case you have only a single instrumental variable. And there has been research which actually talk about the instrumental variables methods and compare to, say, for example, ordinary least squares in terms of whether one is better than the other. So, for example, in this debate, Crown and co-authors in a paper in Value and Health in 2011 noted that Notably, the simulations indicate a greater potential for inferential error when using IV than OLS in all but the most ideal circumstances. And a few years later, Basu and Chan, in a paper in 2014, a couple of years later, referring to the above paper, noted that statements such as these can be quite misleading to the applied researchers who may consequently fail to properly weigh the benefits of an IV approach with its biases. For example, in an empirical situation where the anticipated bias from OLS is large, it should make one more likely to accept less than ideal IVs. So we clearly see that there is no one good answer whether one should be using instrumental variables or not, particularly in cases where the validity of the instrumental variable can be questionable. Okay, so in this paper, what we want to do is provide evidence of and compare alternative estimators which both can be used with or without instrumental variables.
So, Sauvik, can I just interrupt this quickly? This Crown et al., right, 2011, the statement here is saying about inferential error. So does that mean that that has got to deal with the standard error of the IV, or does it have something to say about the actual estimate itself, the coefficient?
Yeah, the point estimate itself, actually, what it is referring to. So it's bias and the standard error, but primarily the bias, because in some sense, the bias, if you think of it, is in terms of it's sort of the primary thing that you're interested, or most concerned with when dealing with, say, instrumental variables or endogeneity problem, right? So, of course, the efficiency of the estimator is also important, but in some sense, the first order importance is in terms of the biasness or consistency of the estimator. Yeah. Okay. So in order to circumvent challenges from using the instrumental variables approach, of course, different other identification methods are also used. For example, regression discontinuity methods and others. But one that deviates from these has been used in prior research, for example, using conditional second-order moments. There is work by Arthur Lubell, for example, where he uses heteroscedasticity moment conditions for identification. So mostly what we learn in econometrics that heteroscedasticity is, if present, it basically affects the standard errors, and there is inefficiency. Basically, it does not affect the point estimates. But then the way we address it is you can use, for example, heteroscedasticity robust standard errors. So that is typically perceived as something undesirable, essentially heteroscedasticity. But in these papers, what they show is that, in fact, if you have heteroscedasticity in your data, that in fact can be used for identification. Okay, so I won't go into these because, so there is a literature on that, which essentially works along the lines of utilizing the second order moment conditions for identification. However, in many applications, they may not be applicable because they rely on some functional form restrictions, which may be hard to defend in specific empirical examples. Okay? So other approaches to identification and direct comparisons of alternative causal estimators, we believe that have not been done adequately, and it remains underappreciated. So what we will do in this paper, in this talk, is primarily compare two causal inference methods in the presence of multiple outcomes. So this is critical because our identification strategy relies on the fact that we have, as we will see, at least 4 or more. So you need to have at least 4 outcomes in order for this method to work, in the sense that I'll get into it in a little bit, but with 3 or fewer outcomes, this method is not applicable. Okay? So we will compare the traditional instrumental variables method along with a shared latent factor model, which can be used for identification even in the absence of an instrumental variable, as long as we can identify the factor loadings through multiple outcome measurements. Okay, so if you think in terms of, so the context that we will be focusing on is a single cross section. It could be also repeated cross sectional settings, but what we will focus on is in terms of a single cross sectional unit. So in that context, how can you address omitted variable bias primarily? Okay, so in panel data context, of course, we know that we can use, for example, fixed effects methods to get rid of endogeneity, which is essentially emanating from unobserved factors, but which is time invariant, right? So for example, if there is one factor which is essentially correlated with your treatment assignment and with the outcome of interest, once you difference out the time invariant factors which may not be observed, those get omitted in the fixed effects regression. However, in the context of a single cross-sectional data set, we don't have any such methods through which any omitted variable bias can be addressed, except through, for example, we know instrumental variables approach can be used, but then we come into the issues of validity and so on and so forth, right? So what we show is that if you have multiple outcomes present, and if you can identify the model, and we will come into the identification in a bit, we show that even without instrumental variables approach, you can get estimates which are in fact reliable, and for which the bias will in fact be less than if you did not have any instrumental variables. And we will use both without and with instrumental variables. Okay, so the metrics that we will use for the comparison with traditional methods will be the bias, efficiency, and coverage probability. So we will use 4 different model specifications. First of all, we will use the naive OLS regression model. Second will be the instrumental variables approach. Third will be the shared latent factor model without an instrumental variable, in which we will in fact use a latent factor which will be shared across multiple outcome equations and the treatment equation. So if you think of it, the idea is that if there is one omitted variable in particular, or it could be, does not need to be a single omitted variable, it could be a factor in fact. Okay? So in that case, within the framework of the shared latent factor model, one can, if you have multiple outcomes, then it's as if you are including the latent unobserved variable as if it were observed. So we are including the latent factor across the multiple outcomes equations and also in the treatment assignment equation. So if in some way you could control for that omitted variable, in that case, any bias emanating from that omitted variable, which is unobserved, would not be there. But in that case, how do we identify the model? So that we will get into. Okay? So this model can be identified without an instrumental variable, as long as we have 4 or more outcome measurements, which we will show in a bit. Okay, and then you can also, if you have an instrumental variable, you can use that in addition to the shared latent factor. Okay, so note that the shared latent factor model only is able to address omitted variable bias. Okay, so if there is, in addition, if there is reverse causality or measurement error, that won't be captured or won't be mitigated using the shared latent factor model. So we can use, in that case, if you have an instrumental variable, even though it may not be a perfect instrument in the sense that if the instrumental variable is contaminated, or in other words, that if the instrumental variable is correlated with some unobserved factors, essentially which may be correlated with your treatment assignment and with your outcomes, even in that case, we will see that we can use the shared latent factor plus instrumental variables approach, and that will improve upon the shared latent factor estimates and also in terms of the efficiency. But it really depends on the degree of contamination, okay? Or rather, the degree to which your instrumental variable can be correlated with your error term. Okay, so we will also look at that. Any questions
Okay.
at this point?
Just one. Do you have any upper bound on the number of outcomes that could be affected?
We don't, we have not, worked that out, but I don't think so. Usually the constraint is in terms of, in practical applications, is in terms of whether you can have, at least 4 or not. The
Yeah,
upper
yeah.
bound, I don't think it's so much of a constraint, at least to my knowledge.
Yeah, so the reason I'm asking this is because, one of the issues that is sort of, it's not really ever addressed, because it's something that's very unique to how this stuff has been used. Let's say you have like a grade IV, then, there are multiple papers over time that will start using that same IV for all sorts of and this was actually pointed out to me by someone who was a co-author who said that at some point in time, you have to stop believing that the exclusion restriction can actually matter because there's like 100 different papers using it for all sorts of so, that kind of so in a sense what you're saying is that when you have a situation like that, this could potentially be useful. So it can't be an IV that's, this would work for these sorts of situations, right? Where you have, these sort of typical IVs that people use for all, for weather related and stuff like that.
Right. So essentially, if you're using, so for example, and we will see one example of an IV, which in fact has been used in the literature, but not in the context of the specific outcomes. Okay. So that tends to happen, right? If you're using an IV in order to estimate the causal effect of, say, mental illness on labor market outcomes, or say, for example, disability, in that large literature, perhaps a particular instrumental variable has been used not for those particular outcomes that you have in your model, but for similar outcomes. Okay, so in that case, we don't know whether the validity of the instrument will be preserved or not, right? So theory can give us some sense of whether it can be used, but for sure, if you only have a single instrument variable, we can never be sure, right, whether that is in fact valid or not, right?
Yeah.
So what we try to show is that if you have some sense about the degree of contamination, okay, and in that case, if you know whether the degree of contamination is very high or very low, or if you have a sense of that, you can, our models, the simulation results that we will show will in fact give us, will inform us as to what model would be appropriate. Okay, but of course, because the latent factor is conserved, and you cannot directly estimate the correlation or covariance between the instrumental variable and that latent factor. Okay, so but you need to have a sense of the degree of contamination, if it's very high, low, or in which range. As long as you can do that, then our models can be informative in terms of whether you should be using, for example, the shared latent factor plus IV model, or the shared latent factor model, or perhaps just the instrumental variables approach.
Okay.
Does that answer your question, Kanishka?
Yeah.
Okay, so let's think of this situation where we are interested in estimating the causal effect of a treatment variable, which we denote by D, on one particular outcome, which we denote by Y. Okay, so this is a very simple framework. We want to, so this is the structural model, right? We regress the outcome variable Y on the treatment variable D. So you can think of the outcome variable as the number of full days of work missed in the past month, and the treatment variable can be mental illness. Okay, so whether you have been diagnosed with any mental disorder or not. Okay, so you can think of this in terms of a dichotomous variable, 0 or 1. Okay, so what we want to estimate is essentially alpha D hat, right? So we know that if the treatment variable D is uncorrelated with the error term epsilon, in that case, alpha D hat will be unbiased, right? However, if D and epsilon are correlated, in that case, the endogeneity issue arises and alpha D hat will be biased and inconsistent. And essentially that is problematic because you won't be able to get unbiased and inconsistent estimates of your treatment effect. Okay? So this is in the case where you have only a single outcome variable. If you think of the instrumental variables approach, that can be implemented as a two-stage least squares. If you have only a single instrumental variable and a single endogenous variable, right? So in that case, the IV estimator is identical to the two-stage least squares estimator. Okay, so in this case, we have a single instrumental variable, so we will use the two-stage least squares approach. The first equation that we have here is the treatment equation, where the treatment variable D is essentially regressed on the instrumental variable Z, right? And you have the error term denoted by omega. And then the second is the outcome equation, where you're regressing the outcome variable Y on your endogenous treatment variable D, right? So the endogeneity arises because the error term omega in the treatment equation is correlated with the error term epsilon in your outcomes equation, right? So extending the example that we have been looking at in the previous slide, that we can think of the outcome to be the same, and treatment variable is also whether you have been diagnosed with any mental illness or not. In this case, suppose the instrumental variable is parental psychiatric disorders for a sustained period of time when the child is growing up or in the formative years of the child's development years. So the rationale is that, so in the psychiatry and psychology literature, there have been a number of studies, and it's widely known that parental psychiatric disorders are correlated with their child's mental health, overall mental health. Okay, so in that case, the idea is that the reason why we choose this as an instrumental variable, which in fact has been used in a number of papers in this literature, is, so the rationale is that parental psychiatric illness is correlated with the child's mental health during the formative years and even afterwards. However, the parental psychiatric illness during the child's growing up years, that should not directly affect the child's adult labor market outcomes once we control for some demographic and socioeconomic characteristics. So you can argue that parental mental illness can in fact affect a child's education, right? Which in turn will have consequences for their labor market outcomes in adulthood. But as long as we are able to control for education, in that case, that does not invalidate the instrumental variable approach, right? However, there may be unobserved factors if they are correlated with this instrumental variable and also correlated with your treatment variable and outcomes, in that case, this instrumental variable would not be valid. So if you think in terms of any mental illness, right, for parents, it's very seldom the case that it's not like other diseases which is easily fixable or treatable. It often there is persistence. For example, if you think of depression or anxiety disorders, once there is an episode of depression or mental illness or a history, then it does not go away very automatically. There are, treatment protocols which can be followed, but then there is a chance of remission. So it may be the case that even when the child has in fact grown up and is working, their parents still may have mental health issues, which in fact can directly affect the child's work outcomes. For example, if you have a parent, you're working and you have a parent who is suffering, for example, depression, or say, for example, schizophrenia, right? If you in fact have to care for your parent, in that case, you may have to take days off from work on certain occasions when there may be a crisis, for example, or you need to take your parent to the doctor in case of an emergency or things like that. So that kind of a direct impact on the outcome, which in fact would invalidate the instrumental variables assumptions, right? So this in fact is not a perfect instrumental variable, as we will argue, but for our purposes this will suffice, because as we will show that even if you don't have a perfect instrumental variable, if there is some degree of contamination, you can actually use the shared latent factor model. But you need to have some sense of whether the degree of contamination, whether it's very high, very low, or somewhere in the middle. Okay. Okay. So I won't go into the instrumental variables approach per se. Most of you will be familiar that in the first stage, we regress the endogenous variable on the instrumental variable and obtain the predicted value d hat. And in the second stage, you regress the outcome on the predicted value obtained from the first stage, right? So in case that z is a valid instrumental variable, in that case, z will be uncorrelated with the error term in the outcomes equation, right? So z and epsilon will be uncorrelated. In that case, alpha d hat, the treatment effect, will be unbiased and consistent. However, if z is correlated with epsilon to a small or large degree, in that case, the instrumental variable is said to be contaminated. Okay, and the magnitude of the bias will depend on the level of contamination. Any questions so far?
Yeah, I just have one thing. So I just wanted to make sure I get this. So you're saying that you need to have some sense of how high there is this level of contamination. So just to follow up on the example that you're using, let's say I was to look at, children that were co-resident with parents versus, where they're not, then I would expect that if your parent is ill, then if you're living with them, it might affect your working hours more than if you weren't. Is that correct? So, right?
Yeah. So in that case, you would think that the contamination would probably be lower for children who are in fact working but not living with their parents. Right? Yeah. So that would be one good example of in terms of assessing the degree of contamination, right? Yeah, that's correct.
Sir?
Yeah, go ahead.
Sir, you said alpha D is unbiased and consistent. Sir, how it will be consistent?
So here we don't show, so consistency is a large sample property, right? So we don't, what we show is using a sample size of 2000, but we use simulations, okay? but it would in fact hold. So if you do any asymptotic analysis, you can, so your question is about if the instrumental variable is uncorrelated with the error term epsilon, in that case, y alpha d hat will be consistent.
Yes, sir.
Oh, so that you can see it's standard. If you look at any econometrics textbook, if you look at the large sample properties or asymptotic properties of instrumental variables estimator, you will get that in, if you have large samples, in that case alpha d hat will converge in probability to alpha d, in fact.
Okay, sir.
Yeah. Any other questions? Okay. So next is, so this is the, so this is not something which is unknown, but in economics, it's not very well known or used very often, the shared latent factor model. Okay, so here the idea is that, so the first equation is again the treatment equation, right? So D is your treatment variable. And now omega, think of this as a composite error term. So the composite error term has two components. One is theta, which is in fact the latent factor, which is shared across the multiple outcomes equations as well. Okay, so if you think of the specific example that we were taking, if you think of theta as self-esteem, okay, which is unobserved and difficult, is not captured in your data set. Okay, however, you have a sense that self-esteem is correlated with your mental health status, and also it affects labor market outcomes and measures of disability like cognitive impairment and social interaction impairment. Okay, so in that case, if self-esteem you're not able to control for in your regression model, that will lead to biased estimates. So alpha d hat will be biased. However, what we show is that in this framework, for now, consider that theta, which is self-esteem in the example, is part of the error term. Okay, but if we are able to control for self-esteem, which is common across the treatment equation and also across the multiple outcomes equations, then any bias emanating from this omitted variable will not be there anymore. But in traditional, when you have a single outcomes equation, you have a single equation model, in that case, there is no way you can effectively control for an unobserved factor or unobserved variable, right? But what we are essentially utilizing is the fact that if you have multiple outcome measurements, and if the omitted variable can be, we will show that if that can be shared across the treatment variable, the treatment equation and the multiple outcomes equations, then any bias emanating from this omitted variable can be controlled for. Okay, so omega essentially consists of this variable theta and the idiosyncratic error term nu. Okay, so delta essentially captures the effect of the omitted variable theta on your treatment variable d. Okay, now consider y to be a vector. Okay, so far we have considered y to be only a single outcome, but now consider y to be a vector. Okay, so think of this as having multiple outcomes. Okay, so at least 4 outcomes we need. Okay, so we are regressing the multiple outcomes on, so we have 4 equations, for example, right? And we are regressing it on the treatment variable d, and the error term, composite error term epsilon, will again comprise of the latent factor theta and the idiosyncratic error term u. Okay, so now think of y as a vector of outcomes, which is at least 4. Okay, and why at least 4 we will get into in a bit. Okay, so think of these 4 outcomes as number of weeks worked in the past year, number of full days of work missed in the past month, with both of which are labor market outcomes, and consider also two measures of disability. Okay, one is a cognitive impairment score and another is a social interaction impairment score. Okay, so all of these are continuous outcomes. And D, again, as earlier, it's the endogenous treatment variable, which is whether you have at least one mental illness or not. Okay, so theta, as I mentioned, is a latent variable. You can think of this as self-esteem, which you do not observe in your data set, but nonetheless, that is correlated with your mental health and also is associated with the work outcomes and the measures of disability. Okay, so here the lambdas and delta, these are known as factor loadings. Okay, so what they essentially capture is the effect of the omitted variable on the outcomes and on the treatment variable. Okay, as you can imagine, theta, because it's not observed, so it does not have a natural scale of measurement, right? So in that case, in order to identify this model, we need some kind of a normalization constraint. So one such normalization constraint can be delta can be chosen to be 1. Okay, so the lambdas, okay, the factor loadings for the outcomes equations, those will be interpreted relative to 1. Okay, relative to this normalized factor. The alternative normalization that you can do is, in fact, you can leave delta free. So you essentially can estimate delta, but then you need to fix the variance of theta, right? Because theta is a random variable. So in that case, you can set the variance of theta to 1. So both are, in fact, can be, so either one, either you set delta to 1 or you set the variance of theta to 1, okay, for identification. Okay, so after that, you can simply substitute the value of the of omega and epsilon in the equations, right? So in that case, D, the treatment variable, can be regressed on theta, and the outcomes can be regressed on the treatment variable D and your omitted variable or shared latent factor theta. Okay, but note that all these equations, so the 4 outcomes equations and your treatment equation, will have to be estimated jointly. Okay, so you can use the likelihood, maximum likelihood approach to estimate, to jointly estimate these set of 5 equations. Okay, now the shared latent factor estimator will be unbiased if this composite error term omega conditional on theta, if that is orthogonal to the error terms in the outcomes equations conditional on theta. So in other words, simply saying that once you control for theta, the error terms nu and u should be uncorrelated, right? So this is a standard assumption that we make, because if nu and u are correlated, in that case, we know that the treatment effect alpha d hat will be biased, right? So once you control for theta, so this is almost like by some magic that we are able to control for an unobserved variable. But the reason we can do that is if you have multiple outcome measurements, okay? Because we will see the identification comes from the fact that you have the number of identifying equations will be more than the number of unknown parameters. Okay, so let's come to the identification part now. Okay, so if you think of the first equation as your treatment equation, okay, so D, suppose we regress that on theta, right? And remember that we've assumed that the factor loading is 1, right? So we will be in fact estimating the variance of theta. Okay, now suppose you have 4 outcomes, right? So y1, we are regressing on the treatment variable D and on the latent factor theta which is common across all the outcomes equations. And of course, it is also included in the treatment equation, right? So now we can in fact jointly estimate these 5 equations, okay? So if you think of this setup, what we are interested in is identifying the treatment effects, right? So alpha 1D hat, alpha 2D hat, alpha 3D hat, and alpha 4D hat, right? Those are the treatment effects that we are interested in, right? And what we want to do is control for the alpha thetas, essentially. Alpha 1 theta through alpha 4 theta, okay? So the number of parameters to be estimated is equal to 9. Why 9? We have the 4 alpha Ds, right? We have the 4 alpha thetas, and then you also have the variance of the latent factor theta, which you need to estimate, right? So 4 plus 4 plus 1. So we need to estimate 9 parameters. And how many estimating equations do we have? We have 10. So if you think of the covariance between each pair, okay, of equations, so covariance between y1, y2, y1, y3, y1, y4, and so on and so forth. If you take all the combinations, then the covariance of y1 and y2 and so on and so forth, all the y's are observed and the d is also observed, right? So the covariances are all observed, and the covariances in fact can be expressed in terms of the unknown parameters, right? So you have essentially 6 covariances, observed covariances between the outcomes, and you have 4 covariances between the outcomes and the treatment variables, right? So in total, you have 10 estimating equations and you have 9 unknowns, okay? So essentially, you can show that you can have closed form solutions of these 9 unknown parameters, okay? So just to give you a flavor of this, how to go about estimating this. So covariance of y1, y2, right? So if you take the covariance of y1, y2, that will be a function of alpha 1D, alpha 2D, alpha 1 theta, alpha 2 theta, and the variance of theta, right? Because the variance of D is known, because D is an observed variable, so you can calculate the variance of that. So covariance of y1 and y2, okay, that will be a function of alpha 1D, alpha 2D, alpha 2 theta, and alpha 1 theta, as well as sigma squared theta, right? Similarly, you will have the covariances for all the other combinations. So essentially, you have 10 equations to solve for 9 unknown parameters, and you can, solving this system of equations, you can get closed form solutions of all the 9 parameters, okay? Now, the necessary condition for identification of this model is that the number of outcomes should at least be greater than or equal to 4. Why is that? So consider the case where you have, say, for example, 3 outcome equations and 1 treatment variable, right? In that case, you can easily show that the number of parameters to be estimated will be in fact greater than the number of estimating equations. So the system will be unidentified. So therefore, you need at least 4 outcomes in order to identify this system of equations. Okay. Any questions so far?
Yeah, can you just go back to the previous slide?
Yeah.
So I'm not sure how you'll get this, because you've got that system, you have 5 equations and you've got, looks like 5 endogenous variables, right?
Sorry, say that again.
You've got 5 endogenous variables.
You have 5 endogenous. No, so the endogenous variable is, so the endogenous variable is 1, right? You have B is the endogenous variable, right?
Mm-hmm.
So you have a single endogenous variable in the system.
Well, even the outcomes are, right? They're typically counted alongside.
Okay, so yeah, okay, so in that sense, yeah, okay.
So this is how is it going to work with the rank? Because you've got one exogenous, 5 endogenous. I don't see how it's going to work with the rank condition. Anyway, we can talk about this later.
Yeah, sure. So in this, if you note that, okay, so these are essentially, so if you substitute the value of B, okay, for example, in the outcomes equation for Y1, right? That will be a reduced form equation, right? Note that Y1 does not appear in any of the other equations, right? So in
Right.
that sense, it is exogenous, all the Y's out.
Right. Okay. All right.
Sauvik, I have a question.
Yes.
So, I mean, I understand this, but this essentially presumes that the unobservable that affects both the treatment assignment and the endogenous variables or the outcome variables is a scalar. Like you cannot have multiple endogenous variables affecting it both, right?
Right. So your question is if you can have more than one latent factor, right?
Right. Yeah. If theta can be multidimensional.
Right. So in this paper, we have not allowed for or considered the scenario where you can have more than one latent factor. Of course, that is possible, right? Because remember that this theta, it does not need to be only a single variable, okay? So it can be can comprise of number of variables, but as long as that can be reduced in terms of one factor, okay, this method will work.
Right.
However, if there are, say you have 5 omitted variables, okay, which can be captured in terms of 2 latent variables, okay, in that case, this model, I mean, this method would not be the most appropriate because we are not allowing for more than one latent variable, which in fact can be there. So if you look at the work of Jim Heckman, Edward Whitlassel, and others, so they in fact extend, they do not use a shared latent factor model, but they in fact talk about when you have multiple latent factors, how to identify such models. Okay, so but that we have not explored in this framework. But then the identification gets much more complex, and identification will be more problematic in that case. Of course, we have not worked that out, but that is definitely a possibility that if you have multiple omitted variables, which in fact do not have one common factor among those, but may have multiple common factors. Yeah.
So just sort of a short follow-up. Suppose I'm sort of I have some data and a priori I may not be able to. I mean, I can have some guess, but I will not know whether theta is unidimensional or multidimensional. So one could be that I assume first theta is unidimensional and use this approach and get some estimates of alphas, and then if possible, if I have, suppose, if my data allows for identification for multidimensionality of theta, then I can sort of see how my alphas change under that sort of multidimensional identification. And if it doesn't change, then I can be more confident that my alphas are good.
Yeah, so you can, in fact, I mean, like you can use, a nested model framework in that case and see, but there the problem is, if you say include 2 latent variables, okay, and you include in all the outcomes equations and in the treatment equation, that will not work. So you can see there is a paper by I think I'm forgetting the journal, but there's a paper by Jim Heckman and his student where they show that how you can identify models in which you have more than one latent factors, and you need to assume there are some restrictions which can be hard to defend. For example, you may need to exclude the second latent factor from one or more of the outcomes equations.
I see.
Right? So in that case, that may be very hard to defend, right? Based on your theoretical considerations. But but those that has been laid out. So that is the challenge. If you move away from the assumption that you have one single latent factor, if you move to 2 or 3 latent factors, then there is some arbitrariness which creeps in terms of how you can identify the model.
Okay, okay, got it.
Any other questions? Okay. Okay, so let me continue. The shared latent factor plus IV model, what we term it as SLF plus IV. So that is a very simple extension of the shared latent factor model, where in the treatment equation, so the first equation, we add an instrumental variable Z. Okay, the rest of the setup is identical. So we have a composite error term omega, and we have a composite error term epsilon, where epsilon is a vector, right? So because these are multiple outcomes, so you need to have at least 4 outcomes. Okay, so in this case, we define contamination in the instrumental variables as follows. Okay, so you have a single instrumental variable Z, and if that is correlated with the error terms epsilon, okay, in that case, we say that Z is contaminated. Right? In that case, the validity of the instrumental, the validity of the IV will be violated. And the way we model this in this framework is that we say that if Z, the instrumental variable, if that is correlated with this shared latent factor theta, right? Because in this framework, lambda theta plus U, which is essentially epsilon, is the composite error term. So if Z is correlated with theta, which is part of the error term, in that case, we say that the instrumental variable Z is contaminated. Okay, so what we will in fact utilize, or rather show, is for varying degrees of contamination. Okay, so by varying the covariance between Z and theta, we will show at what level one model will be preferred over the other. So as you can imagine, if your instrumental variable is highly contaminated, okay, so if the covariance between Z and theta is substantially high, in that case, in fact, the SLF plus IV model will not work as well compared to the SLF model. Okay, we will also show the results from the simulations in that case. Okay, so let me straight away get to the results from simulation. And again, why are we doing simulations? We are primarily interested in the finite sample properties of these alternative estimators. Okay, we are not dealing with large sample properties. The sample size that we are working with is 2000, okay, which we'll see. So we'll take the case of 4 outcomes, continuous outcomes, one single binary treatment variable, one observed continuous control variable X, one latent factor, which is unobserved, theta, which will be shared across the outcomes equation and the treatment equation, and one continuous instrumental variable Z. Okay. So this is the data generating process. Okay. So the treatment variable, so we can think this in terms of D star as a latent variable, which is standard, right? So the latent, so this is like a latent index. So D star, we are regressing. So D star, note that it's not observed, right? So D star, we are regressing on X, Z, the instrumental variable, and theta. And we say that the observed variable D takes on a value of 1 if D star is positive and 0 otherwise, right? So this is pretty standard. And we are assigning the following values for the parameters of this equation. Okay. For example, beta 01, beta x2, beta z3, and beta theta as 2. Okay, so these are the true values. Okay. For the outcomes equations, the following is the data generating process, where we are regressing the vector y which is essentially a column vector, okay, on the treatment variable D, the control variable X, and the latent factor theta, okay. And we are assigning the following values for the alphas, okay. So particularly note that alpha D, which is essentially the treatment effects we are considering. So we have 4 outcome equations. So we have 4 treatment variables, right? So the alpha D's are 2, 3, 1, and 1, okay. The other point to note is that we are, for simplicity, assuming that the effect of the latent variable on all the outcomes are the same. So that is 2, and the effect of the latent factor theta on the treatment variable also is the same. So beta theta is 2, okay. Of course, you can relax the assumptions, this assumption to allow for heterogeneity in terms of the effect of the omitted variable. Okay. So the first case that we consider is the simple case, which is when your instrumental variable is uncontaminated, or in other words, the IVZ is uncorrelated with theta, okay, the latent factor. So in that case, Z and theta are distributed independently and identically, and let's say the mean is 0 and variance 1. Okay, so note that in this setting, we have not set beta theta to 1. Okay, the alternative assumption or the normalization we have done is we are setting the variance of theta to be unit. Okay, so this is a standard normal variable and independent of Z in the first case. In the second case, which is the more interesting case, is when you allow Z and theta to be correlated. Okay, suppose they come from a bivariate normal distribution. Okay, so with mean 0, variance 1, and covariances rho Z theta. Okay, so in this case, what we allow for is a range of values for rho Z theta, or the degree of contamination. Okay, so we take values ranging from 0.01 up to 0.1. Okay, and we will show the results, or essentially the estimated treatment effects, once you vary the degree of contamination from 0.01 to 0.1. Okay, so we are using Monte Carlo simulations. We are taking 1,000 replications, each of sample size 2,000. Okay, so 2,000 is a modest, it's not huge, but in many practical applications, usually this suffices. Okay, so of course you can increase the sample size and see, but what we have considered is a sample size of 2,000, which is a moderate sample size. Okay, and the 4 estimators that we will be comparing is the ordinary least squares, the 2-stage least squares, shared latent factor, and shared latent factor with an instrumental variable. Okay. So before I get into the results, any questions so far? Okay. So in this table, we are showing the simple case, the case 1, which is the case of uncontaminated IV. That your IV is valid, it's uncorrelated with the latent factor. Okay. So what we are reporting is the treatment effect. So note that in parentheses, we have the true values, right? So for the first outcome, the true value is 2, for the second it's 3, and then 1 for the third and fourth outcome. So these are the true values, and we will compare the true values with the estimated values and also report the percentage bias, standard error, and coverage probability. Okay. So the different columns report the estimates from the 4 different models. Okay. So if you consider the naive OLS results, we see that the percentage bias is quite substantial. So the true value is 2 in the first case of first outcome. True value is 2. but the estimated value is 3.8 with a percentage bias of almost close to 90%. Okay. Similarly, if you look at the third outcome, in that case, the true value is 1. However, the estimated value is 2.8 with a percentage bias of more than 175%. Okay. So we see that the range of percentage bias is from, say, about close to 60% to more than 175% in case of the OLS. Now, if you compare that with the shared latent factor model, which does not use the instrumental variable, in that case, the percentage bias is substantially lower, right? So it varies from about 6% to a maximum of about 17%. However, the standard errors are higher in this case. Okay, so in the case, if you don't have an instrumental variable, but if you have at least 4 outcomes, what this result shows is that you are better off using a shared latent factor model, because you will be better off in terms of a reduced bias compared to an OLS model. Okay. Now, if you have an instrumental variable, you can use a 2-stage least squares. Okay. And we compare those results with the shared latent factor plus IV model, where we are also, besides controlling for the latent factor, we are also using the instrumental variable. Okay. So if you compare the 2-stage least squares with the SLF plus IV model, in that case, we see that the SLF plus IV model, in fact, yields lower percentage bias. So for example, in the case of the first outcome, it's 0.19% compared to 0.35% for the 2-stage least squares, but it's also more efficient compared to the 2-stage least squares. So the standard error is 0.12 compared to 0.18. And the coverage probability is quite comparable, so 0.94 and 0.95. And if you look at the other outcomes as well, you will see a very similar picture, or in other words, that the shared latent factor plus IV model yields lower percentage bias and is more efficient compared to the 2 SLS model. So the result here, the takeaway point is that if you have a perfect IV, okay, which is valid, it's not contaminated, in that case, you're better off using a shared latent factor plus IV model. Why is that? Because you're also, in this case, besides using the IV, you are in fact able to control for any omitted variable or variables if that is along a single dimension. Okay, so that is where we have an advantage relative to using only an instrumental variables approach. Okay, so now if you consider the case with contaminated IV, okay, the column 1 and 2, these are just baseline results from the previous table for OLS and shared latent factor. Because changing the degree of contamination of the IV does not affect the OLS or SLF, because we are not using the IV in these models. In the subsequent models, what we are using is we are increasing the degree of contamination from 0.01 to 0.015 to 0.025. Okay, and we are comparing the 2-stage least squares with the SLF plus IV results. Okay, so if you look at these results, as expected, if you increase the degree of contamination, we see that the percentage bias increases, right? So if you look at the 2-stage least squares for the first outcome, the percentage bias increases from 3.25% to 5.06% to 8.65%. Okay, and similarly for the SLF plus IV, we see that the percentage bias increases from 1.74% to 2.5% to about 4%, right? Also, if you note that at all these levels of contamination, which are fairly low, the shared latent factor plus IV, the percentage bias for that model is much lower compared to the two-stage least squares. It's almost half, and it's also lower than the shared latent factor model. Okay, and also if you compare the standard error, we see the SLF plus IV standard errors are lower compared to the two-stage least squares and also for the shared latent factor model. Okay, so at these relatively low levels of contamination, what we find is that the shared latent factor plus IV model outperforms that of the two-stage least squares and also that of the shared latent factor model. Of course, I'm not talking about OLS because the percentage bias is substantially higher compared to all the other models.
So, Sauvik, is there a reason why all these standard errors are the same? Because I'm reading them up on 0.18 and 0.12 for columns 3 to 8 for all the coefficients.
Yeah, so at a higher, I think if you increase the number of decimal points, there is some variation.
Okay.
But yeah. So if you look at, I mean, up to say 5 or 6 decimal points, in that case, there will be variation. But essentially, if you boil down, if you look at 2 decimal places, these are essentially same.
Is there a reason for that? Or, I mean, is that just because of the numbers you've picked? Like, why is that happening?
Yeah, I'm not very sure. So if you look at if you think of the standard errors, right? So yeah, I will need to look at the code, but prior I don't have reason to explain why these are identical, even as you increase the degree of contamination. The percentage bias increases,
Yeah.
but we don't see any. You're right that the standard errors essentially do not change. The coverage probability does, which in fact uses, so you're using the point estimate and the standard errors in that calculation, but the standard errors per se, they do not change. Yeah.
Okay, that's it.
Yeah. Okay. So now, if you increase the contamination even more, okay? So to 0.035 and above, in that case, we see that as expected, the percentage bias increases. But if you look at 0.05, okay, that level of contamination, if you compare the SLF plus IV with the SLF results, okay, so we see that the percentage bias for the SLF plus IV is 8.13% for the first outcome, which is slightly smaller than 8.5% for the SLF model, right? And also, it is more efficient compared to the shared latent factor model because the standard error is 0.12 compared to 0.48. However, at 0.05 level of contamination, the coverage probability drops substantially to 0.73 compared to 0.86, right? And we see a very similar picture for if you look at the other outcomes as well, right? So here, on one hand, we would tend to prefer the SLF plus IV model at any level of contamination less than or equal to 0.05 in terms of the percentage bias and standard errors. But one thing to keep in mind is that the coverage probability drops substantially. However, if you increase it any further, in that case, the SLF plus IV model no longer continues to dominate. And in that case, the SLF plus IV, the percentage bias is lower than that from the SLF plus IV model. And of course, it's lower than the two-stage least squares, right? So 8.5% from the SLF model compared to a higher 12% from the SLF plus IV model and a much higher 26% from the two-stage least squares. Of course, from the SLF model, we see that the standard error is much higher, but again, the coverage probability is about 86% compared to 50% or lower in case of the SLF plus IV, or a very meager 0.17 in case of the two-stage least squares. So what is the, so what do we find overall? That at least up to, so less than 0.05, if you think that the degree of contamination of your instrumental variable is 0.05 or lower, or if you feel that there is quite low, the degree of contamination, in that case, you are better off using a shared leading factor plus IV model. However, if you feel that based on prior literature or your particular data set, that the IV may be moderately or substantially contaminated, in that case, you're better off using the shared leading factor model, particularly because the bias will be lower, and also you will benefit in terms of the coverage probability also is much higher compared to the two-stage least squares model or the shared leading factor plus IV models. Okay. Any questions? Okay. Kanishka, how much time do I have? I think I'm almost, I mean,
Yeah, so we are close to, you can take another 5 minutes, I guess.
5 minutes? Okay, okay. So I'll just give a snapshot. So this is just summarizing the results. So then what we also did, so I'll give you a brief overview of this empirical example, and I'll straight away go to the results. Okay. So in this empirical example, we are looking at the effect of mental illness on work absenteeism and disability among employed individuals. So this is a data, nationally representative data from the US. And the sample size that we have, so we start off with a sample size of 5,692, and we restricted the analysis to those who are currently employed. So our sample size essentially is 3,766, okay? So which is higher than 2,000 in which we had taken in the case of the simulations. And the outcomes that we are looking at, we have 5 outcomes, okay, measures of, so one is a measure of labor market outcome and the others are for disability, okay. So first is number of full days of work missed in the past 30 days and the others are mobility impairment score. So a higher score, it's a continuous scale 0 to 100. It's based on the World Health Organization disability assessment schedule. So 0 indicates no disability, higher 100 is full disability. Okay, so we are using mobility impairment score, cognitive impairment score, social interaction interference score, and a role impairment score. The treatment variable is a binary indicator for whether you meet diagnostic criteria for either depression or generalized anxiety disorder in the past 12 months. Okay, so this is essentially the endogenous treatment variable. And the instrumental variable is what we have considered earlier. So parental psychiatric disorder for a sustained period of time during the child's growing up years. Okay. And we have a number of control variables, including age, race, ethnicity, marital status, educational attainment, physical chronic conditions, and region of residence, which are associated, typically associated with one's mental health and also with the outcomes that we have considered. Okay. So this is a snapshot of the descriptive statistics stratified by whether you meet criteria for mental illness or not, right? So remember that the treatment variable is a binary variable, whether you either have depression or anxiety disorder in the past 12 months. Okay, so among those who have who meet criteria for mental illness, okay, so we see that they in fact fare worse in terms of all the outcomes. Okay, so the number of full days of work missed is 2 compared to 1.1, and it's statistically significant. Mobility impairment score is also significantly higher among those who have mental illness, 4.2 compared to 1.6. also statistically significant, and similarly for the other disability outcomes. Okay, so we see that the individuals with a diagnosed who meet diagnostic criteria for mental illness, for depression and generalized anxiety disorder, they fare worse in terms of the disability measures and also in terms of the labor market outcome of absenteeism. Okay, so overall, the proportion of individuals who have mental illness is 10%. These are all weighted statistics, so these are representative of the US population. And if you consider the parental psychiatric problems, which is the instrumental variable, we see that it is significantly higher. So about 54% of individuals with mental illness have at least one parent who had psychiatric disorders during their growing up years, compared to about 28% among in the control group. Okay, so this is some evidence that we can use this as a relevant instrumental variable. Okay, okay. So this is the snapshot of the results that we have. So this is the effect of mental illness on work absenteeism and disability for the labor market outcome of absenteeism, and also for the four disability measures. So remember that what we are comparing are the estimates from OLS, two-stage least squares, shared latent factor, and SLF plus IV. Okay, so a higher score, essentially a positive score, essentially implies that individuals who meet criteria for mental illness, they have higher number of full days of work missed, and they have higher scores on the different domains of disability. Okay, so this is in the expected directions. So one thing which is very stark, if you compare the naive OLS estimates, these are in fact, the point estimates are in fact very similar to those of the SLF plus IV models. Okay, so if you compare the mobility impairment score, okay, so in the naive OLS, we see that the effect is in terms of 2 percentage point increase, 2.2 percentage point increase in the mobility impairment score from the OLS. The SLF predicts a 2.3 percentage point increase in the mobility score, and also from the SLF plus IV, we find a very similar picture of 2.3 percentage point increase. Okay, the standard errors are also quite comparable between the OLS, SLF plus IV. However, if you look at the two-stage least squares, the point estimates are much higher, and so are the standard errors. Okay, so note that in this case, we are not able to say for sure what is the degree of contamination. But if you look at the literature, in the context of labor market outcomes, although parental psychiatric disorders have been used as an instrumental variable, however, the authors have argued that it's not a perfect instrumental variable. Okay? And the degree of contamination in this case could be quite high. Okay, but then why are the OLS results very similar to the SLF plus IV? Okay, so it is difficult to say for sure, but on one hand, it could be the case that because the sources of endogeneity can be from omitted variable bias, measurement error, or in fact reverse causality, in fact, it may be the case that some of these effects are cancelling out, as a result of which in fact the OLS estimates are not that far away from the SLF and SLF plus IV estimates. However, if you use the IV, and if that is contaminated, if you believe that, in that case, the results, the bias can be substantial. Okay, but the other argument, if you don't want to believe in these results absolutely, you could argue that in fact, what you are picking up in terms of the latent factor is probably junk, okay? And the OLS, if it is severely biased, you are getting severely biased results for your SLF plus and your SLF plus IV results, okay? But based on trial literature, what we have, what we feel is that in fact, the IV may be in fact biased, severely biased. However, the OLS results, so even if you don't use SLF or SLF plus IV, you would get decent predictions from these models. But this is a very specific case. So if somebody is interested in using or applying these methods, I'm happy to discuss in the context of multiple outcome measurements. Okay, so let me end here. Okay, and there is some work which I'm currently performing, but in the context where you have a latent endogenous variable. Okay, so let me end the talk here, and happy to take questions.
Yeah, thanks, Sauvik. So we are almost out of time, but maybe we can take one question if there is any. We asked quite a few, so we've taken up quite a bit of time. Okay, doesn't look like there are any questions coming in, and okay. All right, so let's just formally end it. And